All right. Hey, everyone. So, good morning. This is Chapter 8 Solutions. I've reduced the number of topics in Alex that we're going to need to cover for Chapter 8, but I did want to keep in especially concentration material because that's very important for our future nurses to have at least seen and understand as well as possible because concentration is going to be a big part of what you're doing in the future. So I don't want you to act like you had never seen it before. I have, as I said, I reduced some of the objectives, the things that I didn't think were absolutely necessary for this course. A couple things I left in there because you're going to need to know in the future, obviously, nurses, but those taking 1152 as well. Uh, so if I mention something and say that this will not be on the final or in your Alex objectives, then you can take that to mean you don't have to look at that as deeply as you would some of the other topics. Okay? So if you go to content, I have posted several videos dealing with most of the topics that we're going to look at today. Uh, I try to use different sources, so there's different people on YouTube that teach in different ways, and so if you like somebody like Tyler DeWitt or JG Tutor, then you can go look at their videos and find each one of these more than likely you'll be able to find every one of these topics taught by them as well. So uh, choose whoever that you learn from the best, and then kind of try to stick with them, and hopefully it'll allow you to soak up everything a little bit better. Um, so let's get into chapter 8. I don't want to waste too much time. We got to do some math and stuff today, so I'm going to try to be efficient with my time. This is chapter 8. Let me make sure I got my text ready. Correct. All right. And I'll also probably look at some of the Alex problems just because the way they set it up, I want to explain why they set it up that way, right? Because if you haven't seen this before, you might go in and say, well, what are they asking me here? I'll get to a couple of the Alex problems that I didn't think were difficult, but it just could be confusing in the way that they ask the questions, right? And so, but as I said, I've reduced the number of topics. I think there's only 8 for chapter 8. I could be mistaken about that. It might be 9. But it is mostly everything that you're going to need, especially, like I said, nurses and Chem 1152 students. So, that being said, let's go ahead and get into it and start talking about solutions. All right, solutions is a term that we use for homogeneous liquid mixtures. Uh, so homogeneous, remember, is everything looks the same. Like salt water is a homogeneous mixture of salt and water. I can't tell where the salt begins and the water ends. Heterogeneous means that there's different materials. I can see something different floating around in there. So like oil and water, right? I see the oil floating on top and the water on the bottom. That'd be a heterogeneous mixture because they're not combined. Okay, homogeneous all looks the same. So let's see what else. Pure substance. That just means it is only one element, one compound, um, one material all the way throughout. So salt water would not be a pure substance. Water would be a pure substance, and then salt would be a pure substance, NaCl. But when they're mixed together, it becomes a mixture. All right. And so we just said that heterogeneous does not have a uniform composition, meaning that I can see different particles. I can see flakes of something solid in there, or I can see two different colored liquids, right? So anytime there is a noticeable difference in materials in a liquid, we call that a heterogeneous mixture. Uh, a bowl of cereal, for example, will be a heterogeneous mixture. I can see milk, and then I can see the pieces of cereal. Um, Homogeneous mixtures are, they look the same throughout. So like I said, salt water, sugar water, sweet tea, right? Without ice or anything, just mix up all the sugar, dissolve it, and it all looks the same. But I know that there's water in there, there's tea in there, there's sugar in there, there's caffeine in there. So all of these different things um, are mixed in a way that you can't tell the difference between anything in there. If I pick up any one little spoonful of that sweet tea, I'm going to see a little bit of sugar, a little bit of tea, a little bit of caffeine, a little bit of water, right? All of those um, pure substances are in the one homogeneous mixture. Okay, so these are just terms, and but you will see several questions that kind of ask you to differentiate between a homogeneous or a heterogeneous or a mixture or a pure substance. So it is important that you kind of keep uh, clear which each one of these are. All right. All right. So solution we just said is a homogeneous mixture. It contains small particles, and liquid solutions are transparent. If it's cloudy or you can't see through there, that means that it's not an aqueous solution. It probably has some type of solid particles in there. All right, and there might be floating around the whole thing, like milk. Milk is a good example. Milk actually has a bunch of solids in there, right? If you let milk sit for a while and it curds up at the top, those are those solid particles coagulating, right? So the milk has solid particles all throughout it. That's why it's not transparent, because we can't see through those solid particles. But if you didn't know any better, you'd say milk is a homogeneous mixture, a liquid solution, and for the most part, it is mostly water and liquids and stuff. But all of those small particles are what allows it to block sunlight or not let you see through it, right? So now a couple more terms: solvent and solute. So the way I think about this, water is the universal solvent. It's what we use to dissolve everything else for the most part. Mostly everything else is, we'll talk about like dissolves like here soon. So the solvent I just like to think of is what the main bulk of the solution is. Okay, solute is what is dissolved in solution. So for example, if I were making sweet tea, the water is the solute, and the tea is the water is the solvent, the tea is the solute. The sugar is a solute, right? I dissolve sugar into the water. I dissolve tea into the water. So water is the universal solvent. Um, so always the larger portion of the solution, whatever you have the most of, is going to be the solvent. All right. And it says here, aqueous solution has water as the solvent. The only other things you'll see are nonpolar compounds uh, that can be solvents, but I'll get there in a minute. The best advice I can give for solvent versus solute is whatever the most of, whatever you have the most of is the solvent, and whatever they're the least of, those are solutes being dissolved into the solvent, right? All right. I'm not concerned about colloids or suspensions. Those are having to do with heterogeneous mixtures for the most part. Uh, so milk is a good example of a colloid, right? How we talked about it has particles in there, but you can't tell the difference. So it is a homogeneous mixture, but you can't see through it. Does not settle out. That's a colloid. So there are particles in there that you can't see through. We can still call that a homogeneous mixture. I wouldn't mind if you called it a heterogeneous mixture either, though. Suspension is a heterogeneous mixture that contains large particles suspended in a liquid, so like a bowl of cereal, I think of. I'm not going to ask anything about colloids or suspensions, but uh, it didn't take any time to cover it. So let's just move on from there. Electrolytes and non-electrolytes. So remember we studied ions. I'm going to move you over to the text so I can catch it up too. So we were looking at ions, right? Ions have those little charges on it. Excuse me. Still a little early. I'm still clearing up a little bit. So ions create electrolytes. Electrolytes are any substance that an electric current in water that can move an electric current through water. Okay, you think about batteries or uh, well, several different cases. Almost everything that has to do with electricity has to use some type of electrolyte. You hear it most often when you talk about Powerades and Gatorades, right? Well, those are providing your body with electrolytes so it can conduct electricity more efficiently, right? So, if you don't know, your body uses a ton of ions, sodiums, potassiums. Uh, to do all of these different bodily functions. And so it needs to be able to move electrolytes throughout the body and put them where they need to be so they can help transmit nerve signals or help your heartbeat. Your heartbeat is has to do with an electric potential from electrolytes, a buildup of electrolytes. So these are very important in the body, but let's be more specific about what they are. All right, let me pull my text down to where I need to be. Okay, so definition: substance that contains an electric current in water is called an electrolyte, and one that does not conduct electric current is called a non-electrolyte. And typically, you can tell this just by how they break down in solution. Are they an ion or are they a covalent bond molecule? Right? So we've talked about hydrocarbons. Hydrocarbons are typically non-electrolytes because they don't create that charge. If I put sodium chloride in water, it'll break down into Na plus and Cl minus, and then I have a difference in charge. They can move electrical charges. Okay, the Na will accept an electron, then pass it on. Chloride will accept the electron, then pass it on, so on and so forth. And now we have an electrical current. So these are called electrolytes. And typically, I just look for anything with a charge on it. If something has a charge on it, I would typically consider that an electrolyte, right? Large molecules like C6H10, something like that, that would be a non-electrolyte because those C's and H's don't break down to make individual charged ions, right? So non-electrolytes do not conduct electricity and typically have no charges on the molecules. Electrolytes do conduct electricity and typically are soluble in water, correct? Because water is a very polar molecule, so anything with charges is going to arrange itself like we talked about earlier with distributing the charge throughout the water. Okay? And there's actually an interesting Alex objective. I'm going to try to go there real quick and see if I can't show y'all this problem. Where is that at? Here. And it was like, not that one. Which one was it? Okay, identifying the correct sketch. So, there's another principle in chemistry that we talk about is called like dissolves like. And what that means is that charged particles, okay, water is a polar molecule, correct? Let me pull this up. So it looks kind of like this. I have a two H's connected to an O. While there's not a formal charge on here, these do have partial negative and partial positive charges on them. Okay, and you should already know this. We've went through this before. So anytime I put, say, salt, NaCl, which breaks down into more charged particles, all right, they're going to arrange themselves so that opposites attract, right? The sodium will arrange itself next to this oxygen because the positive and negative pull toward each other, and then the chloride will hang next to the hydrogen because the positive and negative will pull towards each other. All right. So now what this creates is a situation where water will dissolve electrolytes, right? Anything with charges on them, water will actually help to break down and separate in this way right here. Now, so when I introduce something that is, say, not an electrolyte, like a CH4, right? There's not C and H have basically the same electronegativity, meaning they hold electrons about the same. So there is no formal charge anywhere on this molecule. And so when it comes in contact with the water, they just kind of stay away from each other. All right. Now this creates a principle, something in chemistry that we say like dissolves like. Okay. So polar molecules are going to be dissolved by polar solutes. All right. Nonpolar molecules like this CH4 on the top left will be dissolved by nonpolar solutes, so solvents, excuse me. So if I wanted to dissolve a bunch of the CH4 there, I would have to get toluene or something uh, that's also nonpolar. And so just to kind of give you an example, um, so salts I would dissolve in water, like dissolves like. Methane, which is this here, actually that's ethane, uh, would be dissolved in another nonpolar compound. This is called a toluene. Okay, and these are all C's and H's. C, 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 C. So you see it's a bunch of carbons. There is no polarity, meaning that I have a negative charge on this side and a positive charge on this side. These all have roughly the same charge, right? Positive, slightly positive charge. So methane would dissolve in toluene. Salt will dissolve in water. And this creates that principle, like dissolves like. Okay? So, we'll go back to the text and do this little practice problem here. Where's this at? All right, consider the following diagrams for an aqueous solution of compound AB. A represented by red spheres, B represented by blue spheres. Label each as a strong electrolyte, weak electrolyte, or non-electrolyte. Okay? So a strong electrolyte means it dissolves completely and creates a bunch of different charges. So that would be C. C would be the strong electrolyte. A weak electrolyte, it will dissociate a little bit and create charges here and there, but not every molecule will break down to create that charge needed for electric current. So A would be a weak electrolyte, and then B, because it doesn't break down at all, notice how all my blue and reds are still stuck together, that would be a non-electrolyte. Okay, so the same principles you learn when understanding what an ion is, this also creates electrolytes and non-electrolytes because electricity needs charges, needs difference in charges to be able to move. This is what we call an electric potential. So when they start to dissociate, they start to create those charges, and then we have electrolytes. All right, I'm not concerned about equivalence, so we can skip all of that. All right, get the internet back up. Yeah, I'm not worried about equivalence. That's just a way of saying how many charges are on each ion. Remember that like calcium creates a 2 plus charge and then sodium creates a 1 plus charge. So equivalence is just a way for me to keep straight how many charges are available. Okay? But like I said, I'm not testing you on anything to do with that. So we're going to move on to solubility. All right, solubility is the amount of solute, the amount of dissolvable portion that can be dissolved in a given solvent, right? So this is just kind of a uh, mathematical representation. Units are grams per 100 milliliter or grams per milliliter, usually grams per 100 milliliters. And then solubility is how much can be dissolved in that amount of liquid. All right. So, for example, I think about sweet tea a lot. You'll notice I use sweet tea for a lot of my examples. Um, when I go to dissolve sugar in sweet tea, right? If the tea is warm, I can dissolve a bunch more sugar. If it's cold, like I've already put ice in there, a lot of that sugar won't get dissolved. It'll just fall to the bottom. And that is what we're talking about with solubility. Solubility is how much is actually dissolved and spread out in the solution. Okay? Once I start to put the sugar into the tea, let me bring you back here and clear this off. New, don't save. Let me do a little cup here. I'm going to make, oh my gosh, I can't draw. So this is a glass of tea, right? And so I've added some sugar in there. All of this has dissolved. And then my second one, I added some sugar in, and some of it did not dissolve, right? So let's just say I have a little sugar piled up down at the bottom, all right? So once sugar will no longer dissolve, or any solute will no longer dissolve in the solvent, we call that saturated, all right? This one here is saturated. It means it has dissolved as much as it can. It is saturated with sugar, okay? And this can happen in any solution, right? Salt, I can add salt to water, stir it up. At first, all of it will dissolve, and then at a certain point, it won't be able to dissolve any more salt. That is when it becomes saturated, and you'll see salt just start to fall out of the solution and fall to the bottom. Okay, so this, remember, this bottle has sugar in it as well, but I can't see any of the sugar, so we call that unsaturated, right? If everything is still dissolving in the solvent, my tea, then it would be unsaturated. Once it fills up and becomes saturated, these particles will start falling out and become solid again. Okay? So that's saturated versus unsaturated. Saturated means I've dissolved as much as I possibly can. Anything else you put in there is not going to dissolve. Unsaturated, it's still dissolved, and I could add some more and it would dissolve more as well. So I don't want to get stuck on this too long. Let me go back. And as I said, we report it in grams per hundred. Um, and this is what I was talking about, the principle of like dissolves like. So water will dissolve stuff with charges. Nonpolar molecules will dissolve stuff that are nonpolar and does not have charges. So that's why we say like dissolves like. So anything with oxygen or nitrogen is going to be a polar compound and water soluble. All right, that's important to kind of keep in mind. Remember, most of the nonpolar things are going to have C's and H's. Okay, a lot of C's and H's for nonpolar compounds. Um, Still on solubility, nonpolar. So these are the nonpolars. I have used CCl4 to dissolve octane, this large carbon chain molecule. And so when you get to, let me this now I want to go to Alex real quick. When you get to Alex, there will be a problem, something similar to this, and you have to tell me um, which one is being dissolved, or excuse me, which image shows the compound that they have here. All right, so this first one is NO. NO should only have two atoms, right? A nitrogen and an oxygen. And we said that nitrogen is pretty much always dissolved. I'm gonna pick that one. Let me see. Nothing else. So because nitrogen and oxygen are both polar, I assume they're talking about this one. They could be talking about that one. Let's leave that. BCl3, that will not break down because it's nonpolar. So just for the sake of argument, I'm going to do these two. They say VCl3 does break down into solution. All right, so I'm just going to kind of show you what we're seeing here. NO, because nitrogen and oxygen are so close in charge, right? They both have that negative. This is actually considered a nonpolar compound, and so it will not dissolve, meaning it will not break down in solution. Uh, Chlorides usually do. Now, we did see this example here where we had the CCl4, and that was a nonpolar molecule. I wouldn't call this one nonpolar just because it has that V, right? Vanadium. So VCl3 breaks down in solution, dissolves completely, and we have three Cl's and one vanadium, I believe that is. All right, so I'm going to do another problem. FeCl3, that should be polar. NaNO3, probably not as much. So we're looking for something with three Cl's because they've completely dissolved, right? Let's go with that one. And then NaNO3. So NaNO3 is actually going to separate into two compounds. I like this one here. The Na is definitely polar, so it's going to break up, but the NO3 is kind of its own kind of molecule. And just as we said with the last one, N and O, nitrogen and oxygen, are so close in charge that we wouldn't necessarily consider them to be polar when they're connected to each other. Okay? So this one might take you a couple little runs to get used to. Uh, like dissolves like means that it's going to break down, or excuse me, um, polar molecules are going to break down in water to create separate individual ions. Nonpolar molecules are going to stay tightly together because all of this is dissolved in water. These little red and whites in the background all seem to be water. So you're looking for polar molecules that will break down in solution here. All right, let me go back here. I'm not that concerned about the energy of anything dealing with solubility, temperature, and pressure. So increasing the temperature. Make sure y'all can see me for just a second. So increasing the temperature will increase the solubility. This is kind of like with the tea, the sweet tea that I was talking about. When sweet tea is hot, I can dissolve more sugar than when it's cold. When it's cold, the sugar just almost doesn't dissolve at all. It just kind of falls to the bottom of the glass, right? If you've ever tried to mix sugar in with iced tea, you'll see that the sugar doesn't dissolve that easily. So, heat is important for solubility, and that's why typically when they give you some kind of solubility, they'll say at 32 degrees Celsius, at room temperature, at 100 degrees, whatever. Okay, that's because temperature can drastically affect how soluble something is. The hotter, the more likely it is to dissolve. And that goes back to that kinetic motion, right? The hotter it is, the more the molecules are moving, the faster they're moving. So when they collide with water, they break apart more easily the faster they're going. So that's why temperature increases solubility. Pressure also increases solubility. If I increase pressure, Coke is a good example. So in a Coke, when you're manufacturing Coke, you want to get carbon dioxide into the Coke, right? That's the gas, and that's how come a Coke can is kind of pressurized, right? You have to increase the pressure to get the carbon dioxide to stay in solution. And when I crack it, it releases a lot of gas. A lot of that gas is getting released out of that solution because I've decreased the pressure. All right? That's what you're hearing going on. The carbon dioxide is soluble under high pressure. It gets pushed into the Coke, and then once I crack it, release the pressure, it releases that energy. And I can shake it and get it to release even more of that energy, right? I've agitated it, and so now when I release the pressure, it releases more carbon dioxide than normal, right? More than just your little tss, you know, and blow the gas out, and probably a lot of liquid with it because the gas is escaping so fast it draws the liquid with it, and you get those like foamy bubbles from anytime you shook up a Coke too much. You know what I'm talking about. All right, let's see what else we have. um Supersaturated is just a way that I can increase how much I can get to dissolve. If I increase the temperature, I can get it to increase how much I dissolve, like we did with the tea. If I increase the pressure, I can get whatever I want to dissolve more, like we did with the Coke. Um, and to some extent, I can put in more than it would usually take, and we call that super saturated. So when it starts to cool, when that sugar starts to cool, excuse me, when the tea starts to cool, the sugar will actually start to fall out of solution because it was super saturated. It was only taking that much in because I had the temperature so high. And as the temperature cooled, it released some of those uh, sugar molecules. Same with the Coke, right? I have super saturated with carbon dioxide by increasing the pressure. And then once I release that pressure, I start to release some of that carbon dioxide. It's no longer super saturated with carbon dioxide. All right, effects of temperature and pressure. Yep, yep, nope, nope. So there's the Coke example. I've actually never seen this PowerPoint, so that was interesting that they use the same one. It's the easiest one to think about, the easiest one for me to remember. All right, now we have to do concentration. I'm not going to do weight by volume. So any of these you can just go through and work an example problem. Most of them are self-explanatory: volume over volume, weight over volume. So I do the mass over the volume of the liquid, right? The mass of solute over the volume of solution. The volume of solute over the volume of solution. What else we have? Percents, parts per million. This is something that we see later on in chemistry a lot, ppm, parts per million. And this can be mass over mass or volume over volume. Um, that's not the one I'm as concerned about. Molarity. Here's the one that you absolutely need to know. Okay, and if you learn molarity, let me make sure y'all can still see me. Um, you'll have a good heads up onto how to do all of the rest of them. Molarity is going to be, I won't say the toughest, but the most useful. Okay, and therefore it is kind of tough, but nothing that you won't be able to get. All right, so moles, we've talked about moles, right? That's the count of solute over how much volume of solution in liters. So let's do an example problem. Calculate the molarity of a solution from 20 grams of NaOH in 250 milliliters of solution. So they gave me 20 grams of NaOH. I need to figure out how many moles that is. So let me pull up my paint program. Um, Actually, I guess I need to get the molar mass first. Let me pull up this. I can't find it here. Okay, I'm getting this periodic table that they have here. Where's that at? All right, so Na has an atomic mass of 23. We'll call it 23. So I'm going to write all of this on my paint pad real quick. New. All right, so Na equals 23 grams per mole. And then I have to do oxygen. Let me show y'all what I'm doing here. I'm getting the molar mass of NaOH, so I know exactly how many moles 20 grams is. So next up is oxygen. Oxygen has a molar mass of 16. So I'll write that, 16 grams per mole. And H has a mass of 1 gram per mole. Alright, let me bring it over here. So here's where I've written down my molar masses. NaOH. Now they said I have 20 grams of NaOH. I need to figure out how many moles that is, okay? So if I have 23 grams per mole sodium, 16 grams per mole oxygen, 1 gram per mole hydrogen. I can add these up. That'll be, let's see, 39, 40, 40 grams per mole for NaOH, right? And I have 20 grams, so let me make a new one. Bang. 40 grams, and I'm going to put it over 1 mole just so I can keep my unit straight. And then I need to multiply or divide that by 20 grams of NaOH. Looks like divide. Alright. 40 divided by 20 would be 2. But that will leave the mole on the bottom. So that's not the way. I should have done it the other way. Remember, I have to have the unit that I want has to finish up top. So what I should do is do equal blank. Alright. So it would actually be 1 mole over 40 grams. And then 20 grams here. Okay, and then that will leave the mole that I need up top. So 20 divided by 40 would be 0.5 moles. All right, 0.5 moles should be the answer to my oh, 0.5 moles over 250 milliliters. So remember, molarity is moles per liter. So 0.5 moles, and then I want to divide that. Oh, sorry. 0.5 moles divided by 0.250 liters. All right, and so that would be what, roughly two moles per liter. All right, this is my molarity, and that's what you do. Yeah, there it is. 2.0 molar solution. So they go through and they do everything that I just did, probably more clearly. So take your time, and you see how the mole had to be on top, so that mole was on top on the right. That's how come we had to flip that. But you can do that with conversion factors. You can just flip them over and multiply or divide however you need to do it. All right. Let's see. Next up, still molarity. More practice problems. So sometimes they'll give you a molarity. Sometimes they'll give you a mass. You need to be able to go back and forth from mass to moles using the molar mass, how I just did with the periodic table. Molarity, still molarity, dilution problems. Let's do one of those real quick. So dilution problems essentially just allow you to make comparisons between two different substances. So, or say I add water to my sweet tea, and I want to figure out how concentrated it is after I add the water. These dilution problems will allow you to do that. Okay, so there's a general formula that we use, and it's called M1V1 equals M2V2. I'll pull up my paint, get this off. Okay, M1V1 equals M2V2. Okay, now the M, big M, is molarity. So that's what we just learned how to calculate. You need to be able to calculate the molarity of a solution, the concentration of a solution. And then the V is the volume. Okay, sorry, I can't write with my mouse. Y'all know this. So, for example, say I have a glass of water, or let's say salt water, and it is, let's say, 4.0 molar, and I have 50 milliliters of this, okay, and then I dilute it and increase it to, let's say, 200 milliliters. Okay, make sure y'all can see that. Oh, you can't. Okay, let me erase that then. Okay. And then I want to increase it to 200 milliliters. All right. Now I'm not adding any other salt. Uh, I'll put NaCl just so you know that that's what we're talking about. It's 4 molar salt water. Uh, it's in 50 milliliters, and I want to increase it to 200 milliliters. So this will be a dilution problem. I am diluting the original material just by adding water. I want to find out what the concentration of my new solution is. Okay, so what I'll do is I'll set up my problem, M1V1 equals M2V2. Right, M1V1. My first molarity was 4.0 molar. Close that. My first volume was 50 milliliters. Close that, and then on the other side I have M2, which is what I'm trying to solve for, times the new volume, which was 200 milliliters. So let me put that in there. Let me close it off. Divide both sides by 200 milliliters. 4 times 50 is 200, so 200 over 200 on the left, and that'll give me 1 molar. Okay, 1.0 molar technically. 1 molar solution after I dilute it. Alright, so M1V1 equals M2V2. It's one of the easier math problems you'll do in this class. Just make sure that you know how to solve for concentration. M1 is for molarity, and it's going to be important that you be able to calculate that molarity. Sometimes they're going to give you mass, and they'll say, just like we did earlier, 20 grams of NaOH, and you have to figure out how many moles that is. That's 0.5 moles of NaOH, and then you can do the dilution or dissolve in solution. Alright, and then is there anything else that we have to cover? I'm not worried about colligative properties, okay? Boiling point, elevation, freezing point, and I'm not worried about osmosis. So, I think that gets us pretty far down. The only other thing that you kind of need to look at is mass percent. And I didn't see that here in the original text, so I'm going to go to Alex. Where's my Alex at? There it is. There. Next topic. That is a dilution problem. Calculating molarity. Calculating molarity. Calculating mass percent. Here it is. Alright. And so mass percent is actually not that bad. So what you'll do, I don't know if you've done this in a while, probably earlier math classes. Let me pull up my paint program. I'm going to write all of these values down right here somewhere. Okay, so 58 grams water, 76.4 grams acetone. File, new, clear. Let's do that. 58 8.0 grams of water. What else I got? 76.4 gram acetone. I'm just going to abbreviate that. 40.5 methanol. Grams methanol. Alright, so now it asks for the percent composition by mass of each one of these components. So in order to do percent composition, you just added all of these together to get a total mass. 58 plus 76.4 plus 40.5. My total is 174.9. And then in order to find the percent of each one of these, I'll just divide that by the total. So 58 divided by 174.9. Now add that 0 because we want to have the right number of significant digits. 76.4 divided by 174.9. And then 40.5 divided by 174.9. 58 divided by 174.9 equals 0.3316. So I'm just going to write all of as many digits as possible, and then I'll adjust down to the correct number of significant digits afterwards. 76.4 divided by 174.9, 0.4368. And then 40.5 divided by 174.9 equals 0.2316. All right. So now they're asking for percentage, so I need to multiply all of these by 100. Remember, if I want percentage, I need to multiply the decimal times 100. So that would be 33 point. You might not be able to see if I draw those. So I'm just going to rewrite them down here. 33.2% water. 43.7% acetone, and 23.2% methanol. So now these should actually add up to right at 100%. Okay? So I'm going to go put these in on my Alex and check them. Let's see, 33.2 here. What do we say? 43.7 and 23.2. Let's check. All right. So that is percent composition. I think that covers everything we need to look at. As I said, you got the other videos on there, so you can obviously go on there and check out other people and how they do the problems. It's going to be probably pretty similar to this, but I can get a little scatterbrained and jump around a little bit. So let me know if you have any problems. And I've extended the Alex objectives due date till the end of next week because I was so late getting this video in. Got a bunch of stuff going on at my house, but I'll be around all weekend. Let me know if you get hung up with anything and if I can help in any way. So y'all just email me and I will see y'all next week. Bye.